Okay, may I know what we discussed yesterday? Is there anyone or you are not listening to me? Can you repeat? Yes. I guess there is no one in the meeting. Yes, actually, what we did, we discussed the traversal techniques in graphs, like pre-order, post-order, in order, right? Then we discussed some terminology about the graphs, if you remember. Introduction to graphs. What is a vertex, degree, in degree, out degree, edge, path in a graph, cycle, what are connected graphs, what are strongly connected graphs. Then we discuss something about weighted and unweighted graphs. So these were some of the topics that we discussed yesterday, right? Yeah, actually, today we will see how graphs are represented actually. And I've written any program in graphs. So these graphs are actually represented using adjacency matrices and adjacency lists. And may I know what is this adjacency list and adjacency matrix? Yes. Adjacency list and adjacency matrix. Can anyone? Yes. Can anyone? What is adjacency matrix representation of a graph? Why aren't you answering? See, we are now on the verge of completion of the course. You should now answer more. Okay, let me explain it. See, actually, we had a graph. By graph, we mean we have edges and we have vertices. Like suppose I have this graph, A, B, C, D. This is A, B, C, and D. Let me draw one more edge between A and C. So I have to represent this graph. And there are two ways to represent these graphs. One is adjacency matrix and another one is adjacency lists. Right? So how do we represent using adjacency matrix? Let us first check this. See, adjacency matrix is simply a way of representing graph as a matrix of Boolean zeros and ones, we can say, or even we can represent it with the help of weights. For example, if there, let me write some weights: 5, 6, 7, 2, 4. So these are weights, or you can simply represent them with Boolean zeros and ones. Let me first remove the weights, right? Let us suppose, like suppose if there are n vertices in a graph, 4, 5, 6, 7, or anything. So let us suppose there are n vertices. So this uh, graph would be represented with a matrix having n by n dimensions. Like if there are n vertices, so a matrix that would represent this graph having n vertices will be having the dimensions of n by n, right? So it would be a 2D matrix of n by n dimension. For example, we have this matrix, this graph, sorry, and this graph is having how many vertices? It is having 4 vertices. So what would be the size representation of this matrix? So it would be simply 4 by 4, right? And simply if I will designate it as vertex 1, 2, 3, and 4, so it would be like A11, isn't it? A11, then it would be A12, A13, and A14. Similarly, A21, A22, A23, and A24. Let me draw it like this. Like if you have matrix of this, it would be A11, A12, A13, A14. Then it would be A21, A22, A23, and A24. Then it would be A31, A32, A33, and A31, A32, A33, then A34. Then the fourth one would be A41, A42, A43, and A44. So this is the matrix. Adjacency matrix for a graph having 4 vertices is this. Now what are these? A11 and A22 and so on. So whenever there is an edge from vertex 1 to vertex 1 itself, means if there is a loop like this, then we can say its value is 1. If there is an edge between any two vertices, then that value would be 1. If there is no edge between any two vertices, then that value would be 0. So if we write another matrix, value matrix for this, so it would be like, suppose, yeah, there is no edge between A to A, so it would be 0. Now is there any edge between A? It is 1, like suppose it is 2, it is 3, and it is 4. Is there any edge between 1 to 2 or A to B? Yes, so it would be 1. Is there any edge between A1 to 3? A to C? Yes, there is one more edge. Is there any edge between A to D? Yes, there is an edge. Similarly, A to 1. Is there any edge between this to this? Yes. Is there any edge between 2 to 3? Yes, there is this edge. Is there any edge between, no, it is 2 to 2, 2 to, then 2 to 3. Is there any edge between 2 to 4? No, there is no edge, so it would be 0, right? Similarly, is there any edge between 3 to 1? Yes. 3 to 2? Yes. 3 to 3? No. 3 to 4? Yes. 4 to 1? Yes, there is an edge. 4 to 2? There is not any edge between 4 to 2. Similarly, 4 to 3, is there an edge? Yes, there is an edge. Similarly, 4 to 4, there is no edge. So this is the adjacency matrix for this graph. So the graphs can be represented using adjacency matrices. Is it clear? Yes or no? How do we represent a graph? We can represent it using adjacency list or adjacency matrix. If it is clear, just raise your hand. Then we will take another example. Let me clear the screen. Then I will take another example. For example, let me draw a new graph. And you have to represent the adjacency matrix for this. There is an edge from here to here. Okay, let me draw now costs after each. Let us consider this as vertex 1, vertex 2, vertex 3, vertex 4, and vertex 5. This is an undirected graph, or you can draw a directed graph. Now let me draw some, put some weights on this graph with red color. Let us suppose it is 6, it is 7, it is 8, it is 4, it is 9, it is like suppose 10. Now, can anyone tell me what would be the size of the matrix for this? Yes, what is the size of the matrix for this graph? Yeah, 5 by 5. Good. See, it is 5 by 5. Now I have to check what are the different weights. What is the cost from 1 to 1? You write the cost. What is the cost from 1 to 1? Use your chat box. I will make use of it. Tell me the cost. It is actually cost from first vertex to first vertex itself. Right. It is 0 because there is no cost in going from vertex 1 to vertex 1 itself. So it is 0. What is the cost in going from vertex 1 to 2? It is 6. 1 to 3. It is again 0. Are you following it? Just a quick thumbs up. 1 to 4. It is 7. 1 to 5. It's 0. Right? Then second row, vertex 2, 2 to 1, 2 to 1, again it is 6. See, it is an undirected graph. If it would have been directed, then we have to check. Like suppose if the direction was like this, then 2 to 1 would have been 0. 1 to 2 was 6, but 2 to 1 would have been 0 because there was no path from 2 to 1. So as the graph I have taken is undirected. So it would be the 1 to 2 or 2 to 1, both ways. Right? So it is undirected graph. Now what is 2 to 2? Again it is 0. 2 to 3, it is 4. 2 to 4, again it is 0. 2 to 5, again it is 0. Then 3 to 1, it is 0. 3 to 2, it is 4. 3 to 3, it is 0. 3 to 4, it is 8. 3 to 5, it is 10. Yes, then it is 4. 4 to 1 is 7. 4 to 2 is 0. 4 to 3 is 8. 4 to 4 is 0. 4 to 9 is 4 to 5 is 9. 5 to 1, 0. 5 to 2, 0. 5 to 3, 10. 5 to 4, 9. 5 to 4, 0. So this is the adjacency matrix representation of this graph. Right? And hope it is clear. Yes or no? Yes. Is it clear? How do we represent a graph using adjacency matrix? Actually, these 2D matrices are then used to find the shortest path for any graph. So whenever you have to find the shortest path in any graph, the first thing is that we have to represent the graph using adjacency list, this adjacency matrix. Is it clear? Yes or no? Please confirm. Yes. Make use of chat box to let me know whether it is clear or not, or you are audible or not, whether you are listening to me or not. Yes. Only two, three, four people are there or responding. What about others? Okay, there are only two, three people in the meeting who are responding. What about others? Anyways, so this was how do we represent a graph using adjacency matrix, right? Then I will clear the screen. Okay. So this was simply what? Undirected graph. What if the graph is directed? Yeah. At that time, you have to use what? We have to use only the directed edges, the cost of the directed edge only. means either 0, 1, or you can directly put the weight. Now the second representation is the adjacency list. Now what is adjacency list? Yes, can anyone tell me? See, if you know, we make use of array. Array is I can say homogeneous elements, list of homogeneous elements. So we can say an array of lists is used to store edges between two vertices. So whenever there is an edge between any two vertices in the graph, so we can make use of an array of lists. So an array of lists is used to represent this adjacency lists, right? And the size of this array, it is equal to the number of vertices. For example, like in graph we told, if there are n edges, then the size of the matrix is n by n, n by n. Similarly, if you have got n vertices, then the size of array is what? The size of the array is also equal to the number of vertices. Means whatever is the number of vertices, that would be the number of this, the size of the array, right? And one more thing, the index in this array represents a specific vertex in the graph. For example, I will again repeat the sentence. This index in this, because array index is important. So array index, or I can say the index in this array represents a specific vertex in the graph. So there would be a specific index in the graph that will represent what? That will represent each index of the graph. Right? So let us take one graph, simple graph I will take. Then we'll represent the adjacency. It is easy. Let me take this triangular graph like this. It is 1, and it's 2, and it is like suppose 3 or 0. Like suppose 0, 0, 1, 2. Now see, I will make use of this array list. Let me take this as array list. It is vertex 0, vertex 1, and vertex 2. Then we have to check to which vertex is vertex 0 connected. It is connected to vertex 1 and then to vertex 2. Right? Similarly, vertex 1 is connected to 0 vertex and 2 vertex. What about 2? 2 is also connected to 0, then it is connected to 1. So this is the adjacency list that I am using. To which vertices these vertices are connected. So that is simply the list of these vertices. This is called as adjacency list. Or you can say simply how these graphs are represented. Now, like suppose if I will take another graph of same, I will take same graph, but I will make use of direction. Let me take different color. Like there is an edge from 1 to 2, 1 to 0, or I can say 0 to 2. Again, I will make it this adjacency list. So it would be 0, 1, and 2, right? 0 is there, 1 is there, 2 is there. Now, how many this vertices are connected to 0 adjacency list? Nothing, because there is no edge from 0 to 1 or 2. Now, what about 1? 1 is connected to 0 vertex, and then 0 is connected to what? 1 is also connected to 1 is connected to 0, and 1 is also connected to 2. So 1 and 2 vertices are there. Now what about 2? 2 is connected to only 0, because there is only one edge from 2 to 0. 1 is connected to both 0 as well as 2. So this is the adjacency list of vertex this graph. Hope it is clear. So I guess chat box is not working for you. You can directly reply the messages in private chat. Whatever answers you have got, like others are doing. Anyways, so this is how adjacency lists are being represented. right? Okay, hope it is clear. Yes or no? How these adjacency lists are used to represent graphs? Is it clear? Okay, let me first clear the graph, then I will draw one more graph. I don't know why private chat is now this common chat is not working. Anyways, let me clear the drawing, then I will draw one more graph. Let me draw this graph. Let me call it 0, 1, 2, 3, and 4. Can you draw the adjacency matrix of this graph? Then adjacency list is yes, adjacency matrix of this graph. How many you will be able to draw this adjacency list? Adjacency matrix list is very easy. Okay, can you draw the adjacency matrix of this graph? Just write like suppose 0, 1, 2, 3, 4, and what are the connections in zeroth matrix, then one first matrix. Just write 5 rows. If I will write here, for example, you have to write like this. For example, I will be writing, if it is first row, it would be 0, 1, 0, 0, and 1. See, I am writing the first row of the matrix. It would be 1 to 0 to 0 is 0, 0 to 1 is 1, 0 to 2 is also 0, 0 to 3 is also 0, 0 to 4 is 1. So this would be the first row. Then second row of the matrix would be connection is with 1. 1 to 0 is 1, 1 to 1 is 0, 1 to 2 is 1, 1 to 3 is also 1, 1 to 4 is also 1, because with 1 everyone is connected. And what about 2? 2 to 0 is 0, 2 to 1 is 1, 2 to 2 is also 0, 2 to 3 is 1, 2 to 4 is also 0. Similarly, you have to write for 4 and 5. I hope you got it. See, 0 to 4 is 1, 4 to 0 is 1, 4 to 1 is also 1, 4 to 2 is 0, 4 to 3 is 1, 4 to 4 is 4 to 1, 4 to 0, 1, 2 is 0. So you have to write it. 1, 0, 0, 1. Yes. Fifth matrix is 1, 0, 1. No connection with 0. Yes. Yeah. Good. Write for all the matrices, all the rows. So this is the adjacency matrix. Okay. Hope it is clear. Yes or no? Then we'll go to the second part. Okay. Good. Yes.
Yeah, sure, sir. I will enable that. Done. I enabled the chat box for everyone.
Okay. You can now chat in the main chat box, right? So make sure you will not pass any messages to your colleagues, just chat. Otherwise, we'll be forced to close the chat again, right? So I hope it is clear. If there is any doubt, you can ask the question, or you can just type thumbs up if everything is clear till now. Yes. What you have to check the three? What is that three? Can you elaborate, Ashwarya? What is that three? You have to check the three. So for vertex 3, it would be 3 to 0, no vertex, no edge, 3 to 1 is edge, 3 to 2 is edge, 3 to 3 is 0, 3 to 4. So it would be simply yes. 3 to 1, no, 3 to 0 is not there. So 3 to 0 would be 0, then 3 to 1 would be 1, 3 to 2 would also be equal to 1, 3 to 3 would be vertex 3 I am asking about. It would be 0 and 3 to 4 would be 1. So this would be this, right? Okay, let me clear now. So I hope it is clear now. Yes, is it clear? Yes or no, then we'll proceed. Okay, fine. Yeah, then comparison. See, in space it is list. We go B plus C in matrix form. So when we are representing it in the form of list, so the space complexity would be number of vertices plus number of edges. So representing in the form of matrix, it is V square. Because if you remember that matrix multiplication and other things. So whenever we are making use of matrix, so we have to make use of two for loops. So that is why it is coming of the order of V square, right? And suitable for lists. So for lists we have the sparse list, and for matrix it is then. Okay, now there are graph traversal algorithms. You might be knowing these. One is DFS. This another one is BFS, right? So DFS stands for depth first search, and BFS stands for breadth first search. So this BFS is queue based. Always remember it. These are the most of the time the question is being asked. Which among the following data structure is used in BFS? Which among the following data structure is used in DFS? So always remember when it is breadth. Breadth means horizontal. So when it is horizontal, we make use of queue. So it is queue based, isn't it? Or we can say it is level by level. One level, then another level, then another level. So this is BFS. So when it is DFS, D means depth. Depth means vertically. So when it is vertically, the vertical data structure is it is queue, push and pop, right? So when it is queue, sorry, stack. So whenever it is depth, depth means stack. Again, I am repeating. Breadth means queue. So whenever it is depth, depth means stack data structure, right? So whenever there is stack, we make use of recursion. So recursion is used for stack data structure. We have discussed it. We have taken so many examples for it. So recursion is used. So this is DFS, depth. Depth means vertically, depth wise. Breadth means horizontally, level by level. So in this, we are exploring what? We are exploring D paths. Here we are exploring level by level. So the application in this is cycle connectivity check, cycle checking, etc. etc. So this is the difference between. We'll be explaining, if we will get the time, both these algorithms, DFS and BFS. Right? Is it clear? Yes or no? Yes, tell me. Is it clear? Please tell me. Okay, great. Then we'll go to this types of graphs. See, we have so many types of graphs. Depends upon the usability. If we simply go to some of the basic graph types, simply it is directed and undirected. That we have explained. Directed graph is simply a graph when there is a direction on the edges, on these edges of the graph. So when the edges are directed, we say the graph is a directed graph. And whenever the graph is undirected, so it simply means the edges don't carry any direction. So simple, right? So directed graph means when we have the directions on the edges. Undirected graph means when there is no direction on any of the edges of the graph. Then another type is, we call that as weighted and unweighted graph. Weighted graph, yesterday I also told it. Weighted graph is a graph when there are some weights on the edges, or I can say the edges of the graph carry some weights. And these weights can be, they can be cost, they can be time, or they can be other metric, depending upon the problem. Right? For example, like yesterday I told you that you are going from your college to your home. So there might be multiple paths, and it depends. If you some path is taking more time, some path is taking less time, or some path is taking more money, you are consuming much money in order to reach home, and by some other path you are consuming less money, although more time. So it depends. Some people are consuming more money to reach early home. Some people are reaching late home, they are saving money. So this money saving, time saving, and other things, they are simply weights, right? So we are placing weights on the graph. And unweighted graph is simply when there are no weights, there are no cost or time or any other metric on these edges, right? So this is weighted and unweighted graph. Then another type is what? Another type is cyclic and acyclic graph. What is cyclic? Can you write down in chat box what is cyclic graph? Yes. Can you write what is cyclic graph? All edges are connected, right? Anything else? What is a cyclic graph? Starting and end node is same. Okay, fine, good. Anything else? Anything else? Any other definition? Yes, any other definition? Only two people have defined it. What about others? See, simply, cyclic graph is a graph where there are cycles. So what do you mean by cycle? Cycle is simply when the starting and ending vertex is same. For example, if this is a graph, see here, there is a cycle. For example, from this vertex, there is a path, then there is another path, and then this another path back to the same vertex. So it is forming a kind of a loop. Starting and ending vertex is same after coming through several other paths. Similarly, like suppose here, if this is a graph, so if there is an edge bit like this, so it is a cyclic graph, right? So cyclic is simply when there is a loop or there is a circle or a cycle in the graph. That is cyclic graph. Similarly, acyclic graph is what? See here, one more cycle is there, one more cycle is there. Acyclic graph is simply a graph where there are no cycles, where there are no loops, right? So that is the cyclic and acyclic graph. Then there is one more type of a graph, we call that as connected and disconnected graph. Now, what is connected and disconnected graph? Can anyone tell me? What is connected and disconnected graph? What is a connected and disconnected graph? Yeah, try it on chat box. Connected and disconnected graph. I guess I discussed it yesterday also. Every node is connected by edges. Every node is connected by edges. Okay. Yes. Any other? See, connected means what? Every vertex in a graph is connected to one another. Means there is a path between every pair of vertices. Simple. If there is a path between every pair of vertices, like suppose this is a graph. So this is connected graph. Or I can say this is a graph. Let me draw a graph like this. Is this graph connected? Which one is connected? First one or second one? Yes. Which graph is connected? First one, second one? Yes. First one. Okay. Anything else? First one. Everyone is saying first one. Oh, someone is saying both. Okay. Anyone else? Someone is saying no one is connected. How? Only first one. Okay, fine. Yeah. What about others? Which one is connected and which one is not? Mohini, both, right? Only one. Only one. Anush is saying only one. Only one. First is connected linear graph. Okay, what does we mean by linear graph? Let it be. Okay, see, I would say both are connected. If you are here the definition of connected graph, a graph is said to be connected if there is a path between every pair of vertices. For example, see, this pair to this pair, there is a path like this way. This pair to this pair, there is a path either this way or this way. Similarly, this vertex to this vertex, there is a path. So in this graph also, there is a path between every pair of vertices. Although this graph is cyclic, this is not, but this is also connected. as there is a path between every pair of vertices, because it is this undirected graph. So here, if we check from here to here, there is a path. If we check from here to here, this is also a path, like this way, this way, this way, and then this way. So I would say both graphs are connected, right? So I can say that every pair of vertices is reachable from each other, isn't it? Right? So in a connected graph, we have only one component of the graph. Later, when we say about discuss about these undirected, these disconnected graphs, right? Then there is a concept of components in a graph. Hope it is clear. Let me go to that part as well. Let me clear the drawing. So we can reach any vertex from any other vertex by traversing the edges in a connected graph. Right? By disconnected graph, we mean if at least one vertex is unreachable. For example, I have the same graph. Let me draw like the same graph that I was having. This was the graph previously, right? So let me draw a graph like this. So what about this total graph? This is a total graph. See, it has got two components and both the components are disconnected with each other. As you cannot reach this vertex from this vertex. Similarly, you cannot reach this vertex from this vertex. So I would say that this graph is a disconnected graph. So if there is a graph, like suppose this is a graph, right? And here it is, two components. Although the graph should have been like this if there is it is connected. So I have created a disconnected graph from this graph like this. So there is this edge and this graph. So these are disconnected two components of this graph, and both graphs are disconnected. So I will say this is a disconnected graph because there is no edge between this vertex and this vertex. Or I can say you cannot reach this vertex from this vertex. So this is a disconnected graph. So for a disconnected graph, there are at least two or more components. These are called as components. This component is there. Then we have got another component like this. Similarly, in this graph, I have got two components like this, like this. So at least, or I can say this disconnected graph has two or more components. Similarly, if I will create a components of this graph, I can write like this, I can write this, I can write like this, then I can do like this. So it has got how many components? Four components. So a disconnected graph has two or more components. And each component is called as subgraph. You might be, you might have heard about it. A subgraph is a component of a graph. For example, if it was a graph, these are the subgraphs of this graph. So we simply can say that a graph is a subset of a graph, original graph. So all the nodes in disconnected graph, they are not connected. So it is disconnected graph. Or we can say there are two or more components in this graph. Even you can have a single vertex. For example, let me use different color. For example, this is a graph. Like suppose this is graph. And here it can be a single vertex. Like this. It is a single vertex, this. So it is also a disconnected graph. And it has got how many components? Two components. One component is this one. This is one component, and another component is this. So this is all, these are also a subgraph of this graph. So we can simply say that a disconnected graph has got two or more components. Right? Yes or no? Yes. Tell me. Is it clear? Just a confirmation. Yeah, tell me, is it fine? Okay then. Let me clear the drawings then. Okay, then trees have spatial graphs. Yeah, what is tree a graph? Can anyone tell me? Let us discuss this, then we'll go for a break. Is tree a graph? Quickly answer this question. Let us discuss this. Yes, yes, yes. So tree is a special type of a graph. What is the difference between a tree and a graph now? See, tree is a special type of a graph. Is graph a tree? Let me ask you a question. Is graph a tree? Now, where is the difference then? Then where is the difference? Now we have discussed it. You have to be more technically, you have to provide the answer more technically, because we have discussed graph as well as tree. Yes. Can I say graph can be a tree? See, I told you is graph a tree. Yes, graph can be a tree. When? If it is connected, if there are no cycles, and if it has got at least n minus 1 edges for n vertices. For example, see, I have told you, let me write. I have told you like this. Is graph a tree? I can say yes if and only if. When? Number one, it is connected. Number two, has no cycles. And what is number three? For n nodes, it should have it should have n minus 1 edges. So if these three conditions are met for a graph, then we can say it is a tree. Right? Tree is a hierarchical structure, graph is not a hierarchical structure. Okay, fine. It is not always necessary. So what I have written over here, is it true? Then I can say graph is a tree. Yes or no? Okay, so I can say all trees are graphs, but all graphs are not trees. Try to remember these conditions. For a graph to be a tree, it has to be connected, it should not contain any cycles, and for n nodes, it should have n minus 1 edges. I guess these things we discussed yesterday when we were discussing trees. Right? So we can simply say a tree is a graph, or more specifically, I can say when it is connected acyclic and undirected graph. So when it is connected containing no cycles, and for n edges, if it is containing n minus for n nodes, if it is containing n minus 1 edges, then I would say that graph is also a tree. Right? Yes or no? Yeah. So in some exams, you will be asked which among the following graphs is a tree. Right? You will be given some graphs and you will be asked to check which of the following is a tree. Right? Okay. So this was something about trees and graphs. So we can say trees as spatial graphs, or graph is also a tree when these conditions are met. If you have got any questions, you can ask regarding trees and graphs. Yes. Any questions regarding trees and graphs? Example for tree as spatial graph. See, it is simple. I can give you. Any graph you can draw. Where is this? Okay. Is it a tree or a graph? See, it is a graph, but it is also a tree. It is not connected. It is not it is acyclic, and the number of vertices is 1, 2, 3, 4, and number of edges is also 1, 2, 3, 4. So this is also a tree. This is also a tree. Right? So this is a tree, this is a tree, and both are graphs as well. Right? Okay, any questions? Any more questions? Yes. Yeah, let me ask you a question. Okay, what is the minimum and maximum number of maximum, not number, I can say about degree. Yes. What is the minimum and maximum degree? Okay, maximum degree a node can have in a tree. Yes. Write down the answer in the chat box. What's the minimum and the maximum degree a node can have in a tree? Yes. What is the minimum and maximum degree a node can have in a tree? Minimum 0, maximum 1. N minus 1, 1. Good. Minimum 0. How it is possible that a tree can have minimum 0 edge? Yes, what about others? Yeah, what about others? Max 1. Only few people are answering. I don't know why. See, it is simple. Yes, someone has told n minus 1. How is n minus 1? Maximum. Okay, only few answers are there. So let me answer it. It minimum it can have 1 for a leaf node, right? For a leaf node, the degree can be 1, right? And maximum it can have how many? Right, you already told it can be n minus 1. So minimum is 1, max is n minus 1. See, now let me draw a graph. Let us draw a graph. So this is the graph, right? What is the minimum degree for this? It is 1. It is 1. It is 1. So minimum can be 1. And when it is 1? When it is a leaf node. And maximum it can have how many? It can have like this, n minus 1. Like suppose if you have got, this is a tree. Kind of a star representation. 1, 2, 3, 4, 5, 6, 7, 8. So there are total how many edges? What is the degree of this vertex? Maximum. It is if there are 1, 2, 3, 4, 5, 6, 7, 8. So 9 vertices are there. So what should be the degree of this? It is 8, n minus 1. So it can have n minus 1 maximum. And it is a star representation, we call it. So for a graph, the minimum degree is 1 and the maximum it can carry is n minus 1. I hope it is clear and I have shown you how it is. For a leaf node, it is degree is 1 and for this star kind of a node, the degree is n minus 1. Means the number of vertices minus 1 would be the total number of edges. Clear? Yes or no? Okay, one more question let me ask you. Let me clear the drawings first. Let me, okay, someone asking a question, no. Okay, can you tell me which one is taking more space? Tree or a graph? Which one is taking more space? Tree or graph? Which is taking more space? Tree or edge graph, and why? Yes, tree, and why? Yes. Yeah. Which is taking more space and by only two answers I am getting. Graph has cycles also. Graph, favor edges, graph, because it is complete graph. Good. See, if you remember now, whenever we are representing trees, so how do we represent trees? We can represent trees using adjacency list. So same when we represent graph, we are making use of adjacency matrix or I can say adjacency list. And we can prefer adjacency lists because they are memory efficient. Right? And when we represent tree or a graph using a matrix, so we require n minus n matrix, isn't it? So that is why we are just saying we are making use of adjacency lists because in a in a tree, if I will talk about a tree, you can have only n minus 1 edges, isn't it? So we can represent this using adjacency list and the complexity would be simply order of n. But when the same thing is represented using matrix, so for that you require n by n matrix. So previously I also told you for adjacency matrix, the complexity turns out to be order of n square because you would be using two for loops. So it is taking more memory. So this adjacency list is memory efficient and it is preferred, right? In case of trees. And in graphs, it is directed and it can be undirected and directed. And one more thing, like someone answered it in the chat box, it contains cycles, right? And may be disconnected. So the graph structure is complex as compared to trees. And the number of, see here, the number of edges is only n minus 1. But in graphs, the number of edges can go higher, isn't it? And in worst case, if like suppose if you have a graph with n nodes, what could be the maximum number of edges a graph can have? Can anyone? What is the maximum number of edges a graph can have? If you know the formula, it is if there are n edges in a graph, the maximum number of edges a graph can have is n into n minus 1 divided by 2. Simply. Always remember it. The maximum number of edges in a graph can be n into n minus 1 divided by 2. So you have these number of edges in the worst case. So simply when you have these number of edges in the worst case, the complexity can turn out to be of the order of n square. So here it is only n in case of trees because you have only n minus 1 edges at max. So here at max you have n into n minus 1 divided by when it is a complete graph. For example, if you have a graph with 4 vertices, what is the maximum number of edges it can have? It can have 6 edges. 4 into 4 minus 1 divided by 2. So this is the graph it can have. Right? Isn't it? So it can have a maximum of 1, 2, 3, 4, 5, 6 edges. So when we compare this with the formula, this come out to be. Simply if you have a graph of 5 vertices, what is the maximum number of edges in a graph with 5 vertices? Yes. So this can be a graph. 5 into 4 divided by 2. So 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is the complete graph with 5 vertices. So these are the number of edges. So it is complexity, space complexity would be order of n square. So that is why we are just saying that trees are memory efficient as compared to graphs, because graph is a complex structure. Remember it. Graph is a complex structure as compared to what? As compared to these, I can say trees. So graphs can be, I can say like dense. Dense means more number of edges, and it will require n square space, or I can say quadratic space. Fine. Is it clear? Yes. Tell me. Is it fine? Okay. So we can say that graphs are taking more space than trees. Why? Because graph structure is complex as compared to trees. And why complex? Because if there are n vertices, the maximum number of edges a tree can have is n minus 1. And at the same time, the maximum number of edges a graph can have is n minus 1, n into n minus 1 divided by 2. One more thing, graphs can be directed, undirected, cyclic, acyclic. So it turns out to be it is of the order of n square, and for trees it is order of n. So that is why we are just saying that graphs are more complex, or I can say taking more space as compared to graphs. Right? Clear? Just a thumbs up if it's fine. Then we'll go for a 10-minute break and we'll continue after then. Okay. If it is clear, just a quick thumbs up. Then we'll be back with new algorithm. I guess we will start with Dijkstra's algorithm. Let me check whether it is Dijkstra's or any other algorithm. Yeah, Dijkstra's algorithm. Okay, we'll be back at, what is the time? It is 2016. So 2025 will be back. Okay, till then, take a break. We'll be back after Yeah, welcome back. Hope I am audible. Yes. Am I audible? Okay, shall we continue? Yes. See, till now we discussed trees and graphs, right? Then the difference between tree and graphs, isn't it? And which one is better in terms of space? So obviously we checked that trees are memory efficient, space efficient as compared to graphs because graphs have a complex tree structure, right? And the most important problem in mathematics, or I can say in algorithms or in data structures, is the shortest path problem. Yeah, one more thing. Can you tell me before starting Dijkstra's algorithm, what are the different application of graphs? I guess yesterday I also asked you the same question. What are the various applications of graphs? Yes. Data analysis, good. GPS, very nice. Anything else? Computer networks. Anything else? Computer networks, telecommunication. Transport, machine learning, good. Okay, so there are so many applications of graphs in our day-to-day life. Right, let us explain few. See, the very common and I will tell the important application of graphs in social media, or I can say social networks. Right? So, okay, let me use this screen, blank screen. Yes. So, can you tell me how? Let me tell you. See, we all are using Facebook, LinkedIn, Instagram, etc., Twitter, etc., etc. So here you can say you have got a friend or yourself on the Facebook. So consider that friend or yourself as a node. Simple, right? Like suppose we are a node, means any friend of yours, or I can say then a friendship between you and your friend, right? Consider that as an edge. This is friend, your node, then is another friend. So this friendship between two nodes or you and your friend over the Facebook is an edge, right? Then you might have experienced it several times that you are getting what? You are getting mutual friends or you are getting the friend suggestion. This can be your friends because you have got like suppose 20 in mutual or something like that. So that is when you say mutual friendship on Facebook. So that is a kind of an undirected graph because when to be to be explaining it more technically, I can say in Facebook whenever you are getting this mutual friend, that is undirected graph. But in contrary, if I will say on Twitter or on Instagram, there is like suppose when you are friends on the Facebook na, so it is a kind of an undirected relationship. But at the same time on Instagram you have to follow someone, isn't it? So that is one way. Unless you follow back, then it becomes two-way, isn't it? So same time if I will go with Instagram or Twitter, check it. Now I am just telling it more technically. Insta or I can say Twitter. Here the friendship, it is not undirected, it is directed because here is the concept of follow. So when you are following your friend, so it means the relationship or I can say the edge is directed from your end to him. Unless he will follow back, only then it will become a bi-directional. So on Twitter and Insta, it is I can say follow or I can say one way only, or it can be two way. So for the time being, I will say one way follow. So it is a directed graph. But on Facebook, it is what? It is undirected. So the graphs, for example, in case of Facebook, you are getting friend suggestions. Means it is technically checking the graph traversal. So it is, I can say, checking what are the nodes that your friend is connected to. Like suppose if there are so many nodes that your friend is connected to, like this, 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 etc., etc. Then this friend is connected to this, then this. Similarly, so you will get if you are here, right? Like suppose it is you or me, someone is here like some friend, so you will get a friend suggestion of this because it is connected to your friend, so you will get a suggestion of him. Similarly, sometimes you will get a suggestion of him, sometimes you will get a suggestion of him. So because they are connected with your friend, so there is a link between your friend and them, so you might get a mutual friend relationship, or I can say friendship suggestion from these friends, this one, this one, this one, this one, or this one. So because there is a connection, so it is because of the graphs. Similarly, if you see in LinkedIn, you might get first, then second, isn't it? You might have checked it. If you have are using LinkedIn, na, second, then third. So when you have some common connection, that connection is like is having some another connection. Like suppose here it is you are connected with him, and this is connected with some another person, this is connected with him, then that another person is connected with him. So you will say that it is the second mutual connection. It means you are connected with him through someone, and you are connected with him through two people, so you will get second. Similarly, you are connected with him, like suppose there is one more here, so you are connected with him through these two persons, so you will get third. Second, third is coming over there. If I will show you over here, let it be now. I guess it is simple, there is no need to explain this, otherwise I have to open the LinkedIn page. Let it be. So this is how graphs are used in social media, whether Facebook or LinkedIn. And I hope it is clear now what is used. Directed graphs are used in this, in Instagram and I can say Twitter, right? And this on Facebook it is undirected because there is no concept of follow and follow back. Is it clear? Yes or no? Similarly, this was the in this I can say social media, or even you can use this graphs using this na, on internet, or I can say ranking of web pages. And here also you can have you can consider these web pages and nodes. And there are links from one web page to another web page. So those are called as, I can say, edges. For example, you are on www.google.com. That's the node. Now on that google.com page, there is some link. So that link is an edge. When you click on that link, you will go to another page. On that page, there might be some another hyperlink. When you click on that hyperlink, that will land you to some another page. So this way, you are connected to multiple pages through several links. Right? So there also you can say you are making use of graphs. Then more importantly, I can say in GPS navigation system, isn't it? Google Maps, to be more precise. So here also we are making use of graphs, and the graphs used in Google Maps, they are weighted graphs. Can you tell me how they are weighted graphs in Google Maps? Yes, because every time when you are using Google Map, na, it is showing you the time or it is showing you the distance. Means when you are inserting source then destination, right? Then you are selecting the vehicle. Means you can go by walk, by bike, by auto, by like this. So it is giving you the estimated time or sometimes cost. So that is a kind of a weight, or I can say metric, because when you are saying like from your college to home, so when you are typing a vehicle, like suppose bus, so it is showing you the estimated time is, for example, 1 hour. So that 1 hour is the weight metric because it has calculated it by taking several edges into consideration, weights of several edges into consideration. So that's why it is showing you 1 hour, 50 minutes, or any other thing. So it is actually a weighted graph. So here cities or locations or your addresses, they are the nodes, and the roads, or I can say the paths, they are the edges, and distance, or I can say the time, they are the weights. So there we are using multiple algorithms, like you can use Dijkstra's algorithm or any other shortest path algorithm, right? So these are some of the applications of these graphs. Then you make use in like you said, telecommunication. You can make use of these graphs in networking. So there are so many applications of graphs. So these were some of the common applications I thought I will share with you. So is it clear? Okay, then we'll in graph theory or in this DSA, we have so many algorithms for finding the shortest path. So shortest path algorithms are simply the algorithms with the help of which you are finding a shortest path between a source and the destination. Right? And Dijkstra's algorithm is one among the algorithms. And this Dijkstra's algorithm, it finds the shortest path from one vertex to all other vertices. See, one thing is from one vertex to the destination. This is actually a single source shortest path. So it is finding a shortest path from one vertex to all other vertices. Remember it. From one vertex to all other. Don't confuse this now while you are explaining or while you are studying this shortest this na Dijkstra's algorithm. And most of the times what students are doing, they are like uh, misunderstanding it. Always remember this Dijkstra's algorithm. It is a single source shortest path. Single. So I am writing it because you will be able to find it out. Single source shortest path. And it is finding a shortest path from one vertex to all other vertices present in the graph. Remember these points. 2 points are important. It is a single source shortest path, means you are selecting a source and then you are calculating, you are finding the shortest path from that source to all other vertices, not to the destination. When you are saying source and destination, then we are making use of different kind of graphs. Be it traveling salesman problem, be it Warshall Floyd algorithm, be it A star algorithm. So we have other algorithms. When it is single source shortest path, we make use of Dijkstra algorithm. Simple, right? Then that we discuss, it is a single shortest path algorithm from one vertex to all vertices, means finding the shortest path from one vertex to all other vertices. Right? Then see, it does so by repeatedly selecting the nearest unvisited vertex. Means when it is calculating the shortest distance, it is actually selecting the nearest unvisited vertex, then calculating the distance. So that we will be checking with the help of example. Don't bother about that. Then Dijkstra's algorithm is used for solving. See here again, I am writing single source shortest path problem for directed as well as undirected graphs. And by single source, we mean what? One vertex is chosen to be the start. That I already told you. When I say single source, means we are selecting a vertex, right? And this vertex is chosen as a start. And from this start, we are actually calculating the shortest distance to all the vertices, not to one vertex. To all the vertices that are connected with this source. Right? And one more thing, this Dijkstra's algorithm does not work for the graphs with negative edges. Yes. What are negative edges graph, or I can say to be more precise, what are negatively weighted graphs? Yes. What is the negative edge graph? Yes. Am I audible? What is the negative edge graph? Yes. Can you give me the example also? Am I audible? You are not answering. Yes. What are negative edge graphs or negatively weighted graphs? Negative numbers. Okay. Negative edge graph. You are not here. Okay, fine. Okay, let me tell you. See, negative edge graph is a graph where some of the edges are carrying the weights but negative. Means if it is 5, it could be -5. Means negative value. Right? Or I can say simply if the weight is negative. So the weight can be cost, time, distance, etc. etc. Right? Simply if you say, like suppose, for example, you are, let me draw a graph. This is a graph. It is 1, 2, 3, 4, right? Let me consider it as a, okay, let it be undirected. No need to put it directly right now. The cost is 6. The cost is -5, 3 and -2. This is the cost. See, there are two edges of this graph that are containing weights, but the weights are what? Here it is positive weight 6, here it is negative weight -5 and -2. So these edges are carrying the weights, but the weights are negative. Right? So such type of graphs are called as negatively weighted graphs. Simple. So now the question is, when is a graph negatively weighted? Okay, let me draw a new diagram. I guess it was simple. There was nothing. So it is a graph, right? It is vertex A, vertex B, vertex C, and vertex D. Then I am writing the weights of these vertices. Like suppose it is 6, it is 7, it is -3, it is -4. So these are the weights, and some of the weights on this graph are negative values. So when you have a graph having weights as negative, some of the weights as negative, so we call that as negative edge graph. So can you give any example where? Okay, sorry, I'm not drawing it all this. Let me draw this on this screen. Okay, is it clear now? Is it clear now? Image. I have a graph ABCD and I have put some weights on the edges of the graph. Some of the edges are containing negative weights like -3 and -4. So this is a negatively edged graph. Now my question is, can you give any example where you are finding a graph having negative edges? Anyone? Can anyone give me? Profit loss. Okay. See, I will give a practical example. Like suppose, let me think of like this. Like any kind of a shopping or like suppose kind of a discounts. Let me draw another graph. This is a graph. So like imagine we are traveling between cities and there are paths between each city, right? And the cost between two cities, it can be fuel or it can be like suppose whatever you pay means the fare. But let us imagine that some of the roads of this path that are offering some discounts, right? Like suppose let me tell, some of the roads over this path are offering discounts. Okay. Now you have to model this graph, or I can say model these routes, right? Then what will you do? You have these nodes as T's, like it is T A, T B, then it is C, and then it is D. And these edges are the roads between T, like A to B, B to C, C to D, and D to E, D to A, or even there might be some alternate routes as well. Right? Now, see, what are the edges, these weights of these edges? That can be the total effective cost. I can say the total cost. And this total cost will depend upon what? It will depend upon the cost, whatever the cost it has, minus the discount. Like suppose if I can say this B to C, it was having a base cost of 10. But when you go through this route, na, it is offering you a distance of like suppose 20. So what could be the cost of total cost of this route? It would be minus 10. Right. So this way you can get a graph having negative weight. So such type of graphs are called as negatively weighted graphs. Right? Are you getting it? So whenever there are some discounts, so you can say that after calculating this discount, then total weight I am getting or the total cost I am getting is minus 10. Similarly, you can have like for this, for this, for this, and for this. So whenever you are calculating the total for some edges, if discount is more, it turns out to be that the edge can have the negative weight. So such type of graphs, we are just saying that it is a negatively weighted graph. Hope it is clear. Yes or no? Yes, please tell me. Is it fine? Then we'll proceed further. Because these discounts, they are like nowadays they are most often. For example, whenever you are booking any air ticket, you can get a cashback or you can get a voucher, isn't it? So sometimes whenever you are like purchasing something, you can make use of that voucher. So with that, uh, it can form sometimes a negative edge, isn't it? Or sometimes uh, you may get some discount based on the time. For example, like suppose if you visit or you are traveling in a metro on Sundays in Delhi, so you may get a discount fare. Similarly, in Ola, Uber, or in Rapido also, there are some discounts on. It can be any route or it can depend upon the time. So based on time or based on some routes, you may get discounts. So when you make use of those discounts, so sometimes you can get a negative edged weight, right? So this way you are getting but the edges with negative weight. So here actually what we are discussing this Dijkstra's algorithm. So this Dijkstra's algorithm does not work for the graphs with negative edges. That was the point to be discussed over here. So graphs having negative weights, right? They are not being entertained in Dijkstra's algorithm. Let me clear the screen. Okay, so this algorithm does not work for the graphs with negative edges. And for the graphs with negative edges, you can use Bellman-Ford algorithm. Yeah, that we discuss after this. So how it works now? If we had time, okay, we have 5-10 minutes. Let me first give an introduction of it. Tomorrow we'll give an example, and by tomorrow also we have to wind up the sessions as well. See here, let me explain it only in theoretical part. Tomorrow we'll give the explanation. Simple, what we have to do, we have to set the initial distance for all the vertices as 0. So for example, if you had a graph like this, like this. So for initial vertex means the source that you are selecting, right? So for that source, you have to set the distance as 0, right? Clear? First step. And for all the other vertices, we have to set it infinite. Infinite means infinity. Now, what we have to do in the second step? Simple. For all vertices, we have to set 0 for the starting vertex. Like suppose if I go to the next page, here it is. For the first step, what I have to do? I have to select as a 0 for the starting vertex, means the single source. And for other vertices, I am selecting it as infinite. So this is the first step. Whenever you are using Dijkstra's algorithm for a single source, because it is a single source shortest path, select a source. So set a distance, set the initial cost for that as 0, and for all other vertices, set it as infinite. Right? It is the first step. Then, yeah, choose the unvisited vertex with the shortest distance from the start of the current vertex. Means you have got the current vertex and unvisited vertex. So the current vertex is the vertex that is the source. Means for which we have selected 0 distance. Means the source vertex. So we have to select all the unvisited vertices from this source. Simple hai, don't get confused. So from this, select all unvisited vertices. Right? So algorithm will start from this start and it will go to the current vertex. Now, all these vertices we have checked. These are all unvisited. This one is visited, the source vertex. Now we have to check the distances for all these unvisited vertices that are connected with the source. Like suppose if it is 5, if it is 4, and if it is 2. So what we'll do, we are done with this current vertex. Now we'll select among all these vertices, whichever is having the minimum cost. Like suppose here it is 2. Right? And one more thing, once we have selected this vertex and it is checked now, so we don't have to visit it again. Now we have 3 vertices like this one, and this one. And we are checking what? We are checking the vertex with minimum cost. So it is 2. Then from here we are again checking all the vertices, right? And we'll check like suppose if it is cost 5, if it is 3, and if it is 2, or like suppose 3, then we'll calculate the cost, minimum cost with all these. If the minimum cost is less than this or this, then we'll continue. If it is not, then we'll go back and start traversing the minimum among this, like this one. This will become the new source. Then again we'll check. So this way we'll be checking all the vertices recursively. Right? Got it? I hope, I'm sure that you might not have got it, because unless and until we will do the example, only then it will become clear. So simply saying, I was just explaining the steps. Now let us take the example. Let us take it tomorrow, we'll do it again. If you are able to cope it up, then it is fine. If not, don't worry about that. See, as the very step I have discussed, we want to find the shortest path from source. The vertex D I am selecting as a source. So all other vertices, because it is a single source shortest path, and it is calculating the shortest distance between the source and all other vertices. So for that, this example, the shortest path is like suppose D to E, E to C. It is like initially it is checking, then E to C with path 2 plus 4. Like so, for example, if it is like this, D to C for vertex C, if we are checking, the shortest path is like this way. Similarly, if you have to go to this vertex, what is the shortest path? We have to calculate. So with the help of Dijkstra's algorithm, you are just actually checking the shortest path between each of the vertices from this source. So it will tell you what is the shortest path from D to B, from D to G, from D to F, from D to E, from D to A. So it is the shortest path algorithm from single source to all. It is not a source and destination, then it will tell you the shortest path. It is one source and all other destination. Single source to all other vertices. It will tell you the path. Right? Then to find shortest path in Dijkstra's algorithm, we make use of an array with distances to all other vertices. See, there are other algorithms, these are methods that are making use of that heap as well. Then stack, heap stack we call that. Pop and push. I will make it simpler. So here we are actually using what? An array with distances to all other vertices. Like suppose this is an array that will contain the distances of 4, 4, 2 to all other vertices. So here we'll be starting from vertex D0 and we'll set it to 0. Simple. Okay. See here. So initially, as I explained, this is a simple. Initially, I have set it to 0, right? Then after that, So for this distance I have set initially to 0, and for all other vertices I have set it as infinite, isn't it? Because we have not calculated it yet. Now I have to check in the second step here, what are the connected vertices to this source initial vertex. So here if we check, it is A and E. So what we will be doing, we will be now checking the distance between this D to A and D to A. So we will replace these infinite values with their costs. Like here for D to A it is 4, and for D to E it is 2. So vertex A gets the distance changed from infinite to 4. Similarly, vertex E gets it changed to 2. Right? So this till now we did this. Now the next vertex to be chosen as current vertex must be vertex with the shortest distance, like as I already told you. So among these two distances, which one is the current vertex? The one having shortest distance among these two. So here it is vertex D to E, because D to E it is only 2 for the time being. So this vertex E is now chosen as the current vertex. So from yellow it has been changed to green, right? So it is the cost till now, right? Okay. After that, see, it is simple. Now, if we see, let me clear it again. Now 2 is the current vertex. From 2, I am going back to 4 now. The distance to all other are not previously visited. So till now, what are the previously visited? So here I have visited 2 because I have checked it 0 also. Now I am checking for vertex A because E I have visited. Because in the previous step it was 0 to E and 0 to A. So 0 to E was minimum. I have checked it. This was the current vertex. Now the current vertex is 4 because the calculated distance from D to A is 4. And if we check this from D to E then to A, what is the cost? Because it is single source, I have to check both ways. D to A, D to A direct path, and D to A from E to A. So from this it is 4 plus 2 is 6. From this it is 4 only. So I will go with this direct path D to A. Right? So here this 4 becomes the current vertex, and the cost from shortest path from D to A is 4. Right? So I have to choose the lower one. So it will not be updated because initially it was containing like see, if you see, it was D to E, it is 2, and initially D to A was 4, isn't it? Now again I am calculating D to A via E. Via E I will write in bracket. And what is the cost? Via E the cost is 6. Now I will go with the minimum one, so it will not be updated. Right? Now I have to check the next vertex, that is vertex C. So the distance to vertex C is calculated. I can go with via A or I can go via E. So if I will go via A, it would be, because I am at A right now. So it would be 4 plus 3 is 7. So D to C is, if I will go with D to A, it is 7. Right? If I will go like this, see, D to E. D to E is 7 via A. Similarly, D, let me write in smallest, via E. It is what? How much? It is 6. Isn't it? So what is the minimum cost in going from this D to E? Which one? It is 6. So I will update to 6. It is via E. Isn't it? So I am now at vertex C. See here. So C, it has been updated to 6. Right? So 6 I have updated over here. Now, from C, what are the paths? It is C to B and C to F, or even C to G also. Now, let us go by one. I will choose the smaller one, that is C to, because there is only, yes, there are other paths. So, it is 6 plus 2 is 8. And if I will go to here, it is 6 plus 5 is 11. When I will go from 8 to 11, this 8 to F, it is 6 plus 2 plus 2. 6 plus 2 is 8, 8 plus 2 is 10. So after 11, I will update it to 10. That would be in the next slide. Similarly, from here, I will go to G. I have to check so that here it would be 6 plus 5 is 11. From here to here, it would be 7 only. So this way, I have calculated all the paths, shortest paths from this vertex. If it is not clear, I will explain it tomorrow as well. Okay, till now we will conclude the session. If you have any questions, you can ask. But make sure you will recap this on your own, and tomorrow you will come up with questions. And I will again repeat it. If you have any questions, you can ask. Yes. Any questions? Yes or no? Tell me any questions. As we are falling short of time, that is why I concluded over here. Otherwise, I would have explained it. Okay, so let us conclude the session, right? Good night. Take care. Tomorrow will be the last session. You can come up with the questions tomorrow, whatever questions you have. Okay, let us wind up the session.